Okay, so everyone, let's talk today about what? More about efficiency. Okay, efficiency can be defined in one of two ways. Okay, the first one is the ratio of the amount of energy, okay, of the amount of energy, let's say for example, produced to the amount of energy used. So the amount of energy, let's say, used to the amount of energy produced. But what's another word that could be used with energy? No, no, what's another word that is very related to energy but not the same? Work. Work, work, work. Okay? The ratio of the amount of work needed to the amount of work actually done. So the ratio of the amount of work what done to the what? To the amount of work needed. Okay? All right. By the way, can you ever have a machine more than 100% efficient? No, seriously, can you? Can you ever produce a machine that's more than 100% efficient? Nope. So whenever someone tells you, give me 110%, what do you just tell them? Sorry, can't do it. Defies physics. Just tell them. If you're on the like coach on the field, give me 110%. Sorry. Oh, what's the physical? Okay, what's the physical symbol for efficiency? We were okay. Small e or big E? Big E we used for what? Energy. Small e we used. It's usually exclusively used for what? No, no. Forget the for. Sorry. Okay. What about small e? We said that small e is usually used for what? Come on. Huh? Sorry. Oh, just here. Anything with what? Anything for electrons. So can't use capital E. Can't use small e. What can we use? Yep. I'm not kidding. I'm not kidding. EFF. What did they do? It's physicists. Sure, hate us, no problem. We can take it. Okay? Now, can you ever get, sorry, do you think this is efficiency is a scalar or a vector? Again, what did we say about this unit? Almost everything in it is a scalar. Also, if you take a machine and you turn it 9 degrees, do you think the efficiency of it changes? Great, so that means what? No changes. Also, could efficiency ever be a negative number? Can you ever have a negative efficiency machine? What's the worst a machine could get? Zero. If it's not working at all, or if it's what? If you give it some energy and it completely what? Wastes it, what's the efficiency? Hold on. Time cannot be negative. We agreed to that. Can work be negative? Yes. 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 Yeah. Remember, 5 cases, 2 cases positive, 1 case what? Zero, and 2 cases fully negative and partially negative. So work could be what? Okay. How about energy? Energy is a slippery slope to discuss. Can can EK be negative? Can EG be negative? Just because of the physics or the math? Because it depends on the what? It depends on the reference frame I designed. So some energies cannot be what positive because of the math, because of the equation, and some of them what could just because of the way you define it. Okay? But okay, Yasmin is asking, why isn't the 9.8 negative? Okay, 9.8 itself in its own self, is it a negative amount? Not really. It's just what? Meters per second gained every second. Every second. What makes it negative? If you designate the direction up or down to be, remember, it's a vector in nature, so it depends on what? Positivity or negativity of the direction. The magnitude is what? The strength of it is positive by default. Okay? Actually, nothing. Nothing. Nothing in energy is what? Is a vector. However, energy and work depend on what? Force and displacement. So they depend on vectors, but they themselves are scalars, positive or negative. Now you get it. Okay, so remember, efficiency must be a what? A scalar, which means it must have no direction. Okay, and also, if you want to add, it cannot be what? negative. Okay, so let's add this. It cannot be negative. The worst it could ever get is a positive, sorry, is a zero, absolute nothing, and that's it. Okay. Okay, let's go to the next slide. Why are there two equations like power? Because I could define it in terms of what? Ali? Work or? All right, let's do the first one, efficiency. So efficiency, efficiency, I before E except after C. Okay, efficiency. Hmm. Let's do the energy one first. Yesterday we did the work. Let's do the energy one today. The efficiency of a machine or a device or you or your arm lifting, for example, or whatever, the efficiency of anything is energy output divided by the energy what? Input. Times what? You said, what was the unit? Percentage times 100%. If you ever describe a machine, say, this machine is 0.5 efficient. What? Don't say 0.5. Multiply by 100. What's 0.5 as a percentage? 50%. So never say it as a what? As a decimal or as a fraction. Say it as a what? As a percentage. So E, sorry, energy output over energy input times what? 100. 100 what? Percent. You never say just 100. You have to say what? 100%. Okay. So EFF equals, what's the symbol for energy? Capital E. And what subscript should we use? Uh, uh, I like to use OUT because O could look like a what? As zero. Not a big fan of E0. By the way, in university, they use E0 for E initial, like happening at time zero. By the way, get used to definitely a lot of different notation in what? In university or college, because sometimes they don't use initial. They use what? Zero, because that's when you started the experiment. And basically that is what? At time zero of the stopwatch. Again, different notation, same meaning. So I use out over E, what? In times what? 100%. Okay, good. How about the next one? Efficiency, efficiency, also have to spell it, equal. Now, what am I going to use? Not energy. I'm going to use what? Work. I find it endearing actually. Okay, reminds me of like the beaker, the scientist. Okay. Ooh, thank you. Okay. Um, you sure? Okay. No problem. Thanks. Okay. What should I use instead of energy? I should use what? Should use what now? Work. Okay. Done or needed? Needed. What do you mean? I- no, you could. Okay. You could be given the value, or you could be asked for it. But yeah, yeah. Sorry. So I'm just gonna say that this whole thing is a part of the equation. Like, is one variable. Called like energy output is a variable on its own. I'm gonna say something. I'm gonna say something. But this is exactly the disaster with your generation. Is that the phone can't wait. Phones phones and gossip and other people news. Can't wait. Everything else takes a backseat, right? Am I right? I am right. About your life takes a backseat and your future has always has to take a backseat to other people's news, no matter how meaningless it is. It is facts. It is facts, but just listening to the facts doesn't make it worth. You have to work with the facts. By the way, I am bringing some university folks to talk to you because I'm seeing now them almost every day. They're the guys who graduate, and I told them, do not sugarcoat anything, and they will tell you things. Maybe some of you will actually consider, should I actually apply to university this year? And they will tell you things not about the academics, but about the personal conduct. It is sad, pathetic. What is sad? What they're going through in university right now. No one is ready. And forget the academics. They're not ready with the work ethic. And you know what they tell me? Because of the damn phone. I'm just telling you. What's the standard unit? What was the standard unit? Ali said it. Percentage. Oh, sorry, my bad. My bad. The unit is percentage. But what did we do in the equation? What did we divide by what by what? Ah, we divided energy by energy or work by work. What's the unit of these four things? So technically, but it's what? Canceling. So technically, what's the unit of efficiency? Unit or unitless? Okay. But it wouldn't make sense to say this machine is 70 efficiency. It wouldn't make sense. You have no, I know. But technically, if I did multiply by percentage, like the UK or the US or the SOHCAHTOA, it would be what? It would be then what? Perfectly unitless. But I'm making it unit by multiplying it by a what? Because then it makes sense. All right. So it's technically nothing or unitless, since the joules in the numerator and denominator, what do they do to each other? Cancel out, cancel out. Okay. However, by look at the equations, we actually see that the efficiency is actually expressed as a percentage. Okay. Why efficiency can never cross the 100% barrier? Actually, you know what? Here's another question. Why can it not be negative? I mean, we know it has a limit, right? Like a range. Why can't it be less than one side? And why can't it be bigger than one side? Okay, raise your hand. Uday. No, no. I'm asking you not to explain it physically. Look at the equations and reason it with the math. Those are the questions for next year. Yes. Okay, so Omar is talking about what the negativity of it. So can energy be negative in general as an amount? No, it can't. So that means what? All of these numbers, those two cannot be negative. How about work? As again, work could be what? Negative, but as far as what it's related to the what? To the direction, to the direction. But work in itself again is what kind of a quantity? Positive quantity. That's why efficiency could never be what? Could never be negative. Okay, so it could never be less than what? Zero. Why can't it be more than 100%? Okay, interesting. So you're saying what? The way we're defining it is that how much work we what? Need over how much work we actually do. So that means what? If you do exactly as much work as you actually need, what's your efficiency? 100%, because what? You provided all that you need and nothing what? Yes. So that means what? Okay, question. What if you did less work than you need? Do we even ever consider that case? No. We always consider a case where you either do what? At least how much you need or what? Or more. If you do exactly as much as you need, if needed and done are the same, what's the fraction? 1. What's 1 times 100%? you are 100% efficient, which means what? None of your energy went to what? Went to what? Went to waste. What if your needed is slightly less than how much you done? Or what if you did slightly more than you need? What would this fraction be? More than 1, equal to 1, or less than 1? No, no, no. If needed is less than done, or if done is more than needed. If this is bigger than that, that means this, forget the 100. This fraction is a what? Is a decimal less than what? Like let's say 0.99. What's 0.99 times 100? 99%. But that's only if what? If this guy is what? No, no, slightly more than this one. Think about it this way. You're always going to do more than what? Everyone, you're always going to do more than you need. Or you're going to do as much as you what? But here's the thing. Does that ever happen? No. No machine in the universe is what? No machine in the universe is more than what? The 100%. Why? Can someone tell me what means to be more than 100% here? Come on. That means you're what? My output is bigger than what? What does that violate? The law of what? Conservation of energy. Why? Because a system begins with a what? With a total amount finite of what? Of energy. Which means what? Could it ever have more coming from outside? Could it ever have? Again, we're talking about closed system. Exactly. Which means what? If it could steal from the outside, then it could have more what? More output then. And only in that case, your efficiency would be what? What's another case of having more output than input? Is if the machine, weirdly enough, generates its own energy from the what? From the inside. Does that ever happen? So that means what? Can energy ever cross the 100%? Impossible, because that violates the what? The conservation of energy. Also, the same thing for here. Can you ever need more than you do? No, you're always gonna do either as much as you need or what? Or slightly more. That's why those numbers will never be what? Less than 0 or more than what? Or negative. So if you're ever solving and you got less than 0 or more than 100, go back. Something did not go right. Maybe you flipped these two. I don't know. Maybe you flipped these two. Maybe your original equations were wrong. Okay? You are lifting a what? You're lifting a box with a mass of 7.3 kilograms for a distance of how much? 53 centimeters. So about what? About half a meter. From here, this much. This much. Okay? So I'm lifting it. Let's say center of mass or base. The base has to make it from 0 to what? 53. Okay? 0 to 53. Just that. Okay? All right. Well, if I just told you you lifted it, did I tell you how you did it? No, I just know that you moved it from here to here. That's it. I can tell you that someone is watching you what? Your motion, or the box's motion, I should say. It tells you that the box under your force was what? Which direction? At a what? Of 35. What does this measure? Ah, okay. Question one. Question one. The question is just what? How efficient are you? Okay. What did I say the formula for efficiency was? I gave you two. One of them has work in it, and one of them has what? Do you think we're going to use the work equation here or the energy equation? I've got myself distance. Also, how do you lift a box? Using your what? Applying a what? Guess what? You cannot do this problem unless you do force analysis first. So I have to sketch a what? Thank you. Okay, everyone. Let's sketch an FBD on this slide. Okay. What's the first force definitely on the box? So F applied. Okay. Which way? Come on. Which way is it moving? Up. Thank you. Yep. Is this Newton's first or second law? Why? Because it's telling me it's what? What if it told me you are moving it up at a constant motion? There would be an example of what? Newton's first law, which means then you perfectly what? Modulated or controlled your applied force to exactly equal what? Fg, and you made it what? Cruise control all the way up for 53 centimeters. But you didn't. Okay? What's Newton's second law? The famous one. F net equals ma. All right. So now we go to the next slide, everyone, the blank one, to do the math. All right? Exactly. Let's do it when we do the math. But you're absolutely right. Why? Because what's the unit of G? 9.8 what? Meters per second squared. That's it. All forces has to be done in meters per second because G is given to you in meters. Perfect. Good observation. So go ahead. Okay. F net. My bad. F net. By the way, is this a one-dimensional or two-dimensional problem? Yeah. Do you see any other forces on some other axis? No, there isn't. So F net, yes. F. By the way, to Muhammad's point, what did you call it, Muhammad? What? The y-axis? Just be prepared in university for some teachers or some profs to call that the what? The x-axis. Again, because hold on. You are still fixated on the what? On the math thinking. That whatever goes up and down is by default the what? Well, I have a proof against that. It's actually neither the x nor the y. It's the z. Think about it. X. You see, you're fixated on one way of seeing it, but you need to be what? Open to what? Open to multiple ways. In 3D, what is this one? So, this one is no, this one. X, Y, and this one is pointing up. So you see, you can call it anything you want as long as you know which one it is. So in university, they will actually call it what? They will actually call it what sometimes? The x-axis. Who cares? We only have one. So that means we can call it what? Anything we want, right? That's all. From the FBD, what does FNet break down to be? Which one is positive? Yeah, good. So positive F app. Say again. Well, you know what? Let's write and see which ones we know and which ones we don't. Minus FG equals. Okay. What's FG all the time? MG. Did someone say 9.8? Because again, remember, if I ask you what's FG and you just say 9.8, that is wrong. That is not FG. That is just the what? The G. The gravity acceleration. I'm asking you for the gravity force. Force. So F app minus what? Mg equals what? Okay, what do I know about out of all of these? Do I know the mass of the box? Do I know the G? Do I know the acceleration? In what though? In centimeters per second. Okay. So the only thing I have to solve for here would be what? Great. So let's plug in the math now. So I'm going to move this guy here. So equals MA plus MG, which is what? M on the out, A plus G. All right, let's do the math here. I think the mass is 7.3. Now, what would 35 centimeters per second squared be in pure meters? Because you divide by 100. Thank you. So 0.35 plus 9.8. Wait, like the whole thing? Okay, 74. Okay, hold on. Technically, are we done the problem or are we still doing intermediate? So, all right. Mm, always. Why? Because then you guarantee that that your error in the final answer doesn't really suffer because of that. So 74 point. Did you say what? In what unit? Nice. I'm still doing force analysis, Newton. Okay. What is the question asking for? How what? How efficient? Now let's do what? What's up? Here, go ahead. Now let's do the what? Let's do the efficiency equation. What's the efficiency equation? Do we have enough? Okay, everyone, let's now go to this slide. Sorry, everyone, let's now go to the. So this slide was for what? FBD. This slide was for the force equation or the force work. This one is the what? For the work. Okay, everyone, what's the equation for efficiency if I use work? Work what? No, not out. No, no, that's energy. Good. Everyone, let's go back to the slide. Okay. How many forces do I have? Which one of them is related to the work you did? The G or the applied? Nice. So that means what? To find the work you did, you're going to use which force? And to find the work you need, you're going to use what? Okay. The work that you did came from which force? So that means what? If you're going to calculate the work you did, you have to use which force? Applied force. How many other forces are left? Fg. So that means what? The work that you needed to do theoretically is not related to how much force you applied, but it's related to how much force of what? Gravity resistance or gravity. Do you see what I mean? The work you need does not depend on you. It depends on the what? The situation itself. It depends on the other player trying to what? Slow you down. So the work needed relates to what? Gravity. The work done relates to what? Which force? Which force? Applied. There you go. So now let's what? Let's calculate each one on its own line. Oh, my bad. Sorry. Okay. Okay. So everyone, let's go. Okay. Okay. Work. Which one do you want to do first? It doesn't matter. You have to do both. So that means the work what? Needed or done? No. If he's doing force applied, done. So work done. Okay. Everyone, what's the equation for work? The three things multiplied together. The first thing I taught you in this unit. Before that, come on. Force. Exactly. So force applied times distance times. Huh. Okay. Did we figure out how much force you actually applied into the system? How much? 74.1. Okay. How much distance did you move it up by? By five. So what about the 35? What was the 35? 35 was the acceleration. 53 was the what? By the way, that's why I gave you that number. 53 and 35. So, but I have to convert it to what? Meters. Cosine. Tell me what's the angle between the applied force vector and the motion vector? They're going together. How much? Two parallel vectors have how much angle between them? Why? Because it's case number what? 1, 2, 3, 4, 5. Case number one. Case number one is perfect parallel. It's the what? It's the max positive. You got it. So cosine of what? 0. What's the good news about cosine of 0? It's a what? It's a positive one, which means yes, 100% what? You're using that force to lift the box up. Okay. So I'm just gonna not bother you with this one. Just put +1 here. So I need someone to multiply 74.1 times 0.53. You gotta be very close to 37. Exactly. It's slightly more than half of this. 39.3 joules. Yes. Okay. How about the work needed? Oh, that's just the value of cosine of 0. Cosine of 0 is by default from grade 11 12 functions, positive 1. Okay. How about the W needed? I'm going to use the same equation, but I'm not using F applied. I'm using which force? The one going against me. Fg times delta D times cosine theta. Okay, come on. What's Fg again? Mg. So Mg times delta D times cosine. Now, how is on the FVD, everyone? How is the Fg and the motion related? Are they going together or perfectly opposite? What's perfectly opposite as an angle? 180. And guess what the cosine of 180 is? -1. It's the complete opposite case. So cosine of 180. What? Where am I? I need people to ask now. Yes, Walid, what's up? Huh? You mean this one right here? Okay. Do you agree that the needed work is related to the FG? Okay. What is FG in any physics course you ever take? That's it. Good? Okay. Let's multiply four numbers together. And what? Hold on. Love that question. We are going to get a negative work because this is going with the system or against the system. But then, do we ever take negative in the final efficiency calculation? No, because we relate. Do we relate the signs or just the amounts? Just the amounts. But I still need to see this calculation. You see my point? I still. Yes, so you take the absolute value of it basically in math terms, okay? But I still need to see the negative in this calculation. So what's m? 7.3 times 9.8 times 0.53 again times what? Oh, no need for times. This is how much? Thank you. So no need for a times sign. That will be negative something. Go for it. 37.9. Also in what? In joules. Finally, we can do the what? The efficiency. So last calculation. EFF equals. Which divides which? Why can't you divide the 39.3 by 37.9? Because then you would get more than what? 100%. So even if you don't really understand which one divides which one, at least know you can never get more than what? 100%. So you divide the small by the big. So 37. Am I missing anything from the 37.9? I'm missing a what? But on purpose, because my efficiency could never be what? I'm just comparing the work amount divided by 39.3 times 100%. So that's actually pretty efficient. Look how much work you're burning. Everyone, you're burning how many joules? You're burning 39.3 joules. You only needed to burn how much? So how much extra are you burning? Extra. Not even 2 joules more. About like 1.7. No, not 1.4. You are just putting an extra 1.4 joules in. That's my point. That's why your efficiency is what? Quite high. How much is it? 90 what? Okay. What's the sig fix situation now? Okay. Tell me what sig figs in the problem. Hmm. 7.3 is 2. 53 is 2. So to 2 sig figs, what is your efficiency? 96%. You don't use it, you lose it. Practice.